So we're continuing on with confidence intervals. And we saw with the first lesson what a confidence interval was, like what it looks like, how we sort of interpret it, that it's a range, and we were talking about proportions so far. We can do means, but we'll do that later. How confident we are, or yeah, a percentage confidence in one number to another number that our sample proportion will capture. Okay. So like if we say, what did we have? What was the, oh, it was the election result, right? And we came up with a confidence interval of 0.32 to 0.72 voting for the Democrat. And so what that means, depending on the confidence level, and we started with 95%, we can use other percents, for 95% confidence that between 0.32 and 0.72, or 32% and 72%, will represent the true proportion that voted for the Democrat. So let's look at another example, water safety. So how do we use our home's water? What do you use it for? Shower. Drinking. Laundry. Dishes. Showering. Laundry.
Water in the glass.
Dishes. Water in the grass, absolutely. And then in this one, drinking. That's good. That's lots. So obviously, we want our drinking water to be safe. Okay. So in Canada, that's mainly the priority of the or that's mainly the area of the provinces and territories. Okay. The big issue is there's still a lot of homes, older homes, obviously, where the water flows through lead pipes. And lead pipes, depending on how much lead gets into the water, can cause several different types of health problems. So problems with the heart, problems with kidney, problems with intellectual functioning even. Okay. So too much lead in the water could cause things like that. So they've established that the amount of allowable lead in drinking water must be 0.005, yes, milligrams or less. Okay, so you take a liter of water out of a lead pipe, measure the amount of lead in it, and if it's less than 0.005, it's deemed safe. If it's more, it is not deemed safe. Okay. Just as an example, you can find this information. So here, this is in Fort Rouge, East Fort Garry. Okay. Notice that at the top it says there's about 2,500 homes still with lead pipes. Almost 11% of all homes in Winnipeg with lead pipes. So they took a sample, and you can see like there's different sort of levels, okay? Where if you're turning on the water for 1 minute, if you're turning it on for 2 minutes, if you're turning it on for 5 minutes, generally the longer you leave it running, the less lead that there's going to be because it gets flushed through, okay? So we can see the ranges here. Remember, it's 0.005. Everything looks underneath here on average, okay? But that doesn't mean that every single home is below 0.05, because you can see here, just with a random turning on the water, 15.1% of the homes has greater than 0.05. That goes down to 0 if you let it run for 5 minutes. Okay. So that's in Canada, but there was sort of a famous situation, I guess you could call it, in a town called Flint, Michigan, that lasted for a couple of years, where there was a real crisis with the safety of the water. And there were real issues as to what the government was doing, saying that it's safe when it actually wasn't. Okay, so in the States, the EPA makes regulations regarding safe drinking water. So they have a slightly different rule. They say no more than 10% of households can have prominent lead levels, 15 parts of lead per billion measures of water, I guess. I'm not sure what exact you'll measure with the ounces. Okay. So if you failed this rule, and if this lasted for a couple of years, like, what would you have to do? How would you survive? Like, you can't, you just mentioned all the things you can do. Well, how could you get safe drinking water? Yeah, I mean, it would have to be all bottled water, all imported from other places. And that gets very expensive, okay? Or filtered water from other places, because you couldn't use the water in the town. Okay? So you would have to use, I'll just say bottled water. For all of the above, meaning at the top. Uses. So this is actually a really good statistical problem, because we obviously can't do the entire town and measure the amount of lead for the entire town, because that's a lot of homes. And I mean, I suppose you could, but it would take a very long time and be very expensive. So we want to take a sample and see how well that sample represents the actual population. And you can see this thing lasted for almost 2 years. Or sorry, it lasted for over 2 years. And 12 people died because of Legionnaire's disease. Okay. And there were also a lot of sick people. Okay, so how did the researchers and citizens use stats to hold Flint officials, that's government officials, accountable? There was a doctor from Virginia Tech University who randomly sampled homes, tested each home's water for prominent lead levels, and they sought to determine if Flint was actually failing the EPA no more than 10% rule. So we're going to sort of model that. And there was an applet you could have used, but to save some time, like it gives you a map of Flint, and then you just click random sample, and it'll give you a random home and tell you whether it has prominent lead levels or not. So I tried that, and I ended up with 18 out of 50 homes that had prominent lead levels, which means 32. I took a sample of 50. Okay. Which would be well under 10%, but that's one of the conditions we'll talk about later. So that's what we got. So remember, according to the EPA, no more than 10% of a city's homes can have prominent lead levels. Does our sample suggest that the city may be violating this rule? It does. Okay, so yes, because our sample proportion, which we'll just go short for p hat, was 18 out of 50, which is 36%, which is definitely greater than or equal to 10%. But does it prove it? Does one sample prove it, or do we have to do more work? Don't we have to do more work? Isn't that what we did sort of in the previous lesson? Okay. Because maybe we just got this by chance. So no, because P may have occurred by chance. Okay. I mean, maybe we get some similar results by chance if we took more samples. But in order to determine that, we actually have to do it. We have to take several samples, and then we have to average those proportions, and then calculate the probability. So more study is needed. So in this study, or in this situation, what's the population? What's the population? All homes wins. And a sample, which was 50. 50 randomly selected. So what's the parameter? Well, remember, for the population, it's just when we're talking about proportions. For the population, it's just P, but for the statistic, it's P hat. So this is the true proportion of homes. Prominent lead levels. Okay. And this is the proportion of the sample. Prominent lead levels, which actually turned out to be 36%. Okay, so this is where we go ahead and do the whole big study. Okay, let's just assume. Oh no, we can. I'm not going to write them down, but we can talk about the conditions. Okay, so remember, to determine the confidence interval, we have to use normal distribution, so it has to be normal. Okay. Either by you're told that it's normal, or by the large counts, not large sample, that's means. Okay. Then we can say that if we took several samples, the average of those samples can be said to be equivalent to the single proportion sample we got. Because we saw that this was a good estimate. And then this is a little bit new. Well, this is new. not a little bit. We don't call it the standard deviation anymore. We don't use sigma. And the reason is, and this stands for standard error, is because we're no longer using, we no longer have a population standard deviation. We're using the standard deviation of the sample. So we can't use the sigma notation, which is why we use this. Just sort of a notation thing. But the formula is still the same. We still take the sample proportion times 1 minus the sample proportion divided by the sample size and take the square root of it. So for the time being, we'll list the conditions later, but let's just assume the conditions. Okay. So in this situation, we've got a normal distribution. If we took several samples and averaged them, it would be the same proportion as our single sample. 0.36. To find the standard deviation of the sampling distribution, we take the square root of 0.36 times 1 minus 0.36 divided by the sample size, remember, which was 50, and we get approximately 0.07. Okay. So remember, we're going to use normal CDF, so we need an accompanying normal distribution. So we're going to draw our normal distribution of the sampling distribution. Okay. So these represent all the sample proportions we got, or p hat. And the mean was 0.36, and then we keep adding 0.07 to the right, subtracting 0.07 to the left. So we get 0.43, 0.50, and 0.57. And we get 0.29 going the other way, 0.22, and 0.15. So our mean was this, but because we take several samples, there's going to be some variation. Okay, I want to count for 95% of it. Well, 95%, we learned earlier in the year, was within 2 standard deviations of the mean. But I told you technically it's not 2, it's 1.96, so it's a little bit less than 2. And I'll explain where that comes from later. So we'll just sort of put that slightly inside the notches, because it's not quite 2, it's just a little bit less. And this represents 95% of the area, so it's going to be 95% confidence interval. That our sample proportion captures the true proportion from just a little bit above 0.22 to just a little bit below 0.5. And to figure that out, and you will get this formula always. Remember to calculate a confidence interval. We take whatever the point estimate is, as in p hat, in this case, or x bar if it's a mean, and we add and subtract the I'm missing something. The margin of error, yeah, actually, no, margin of error. So remember, our point estimate is 0.36. To find our margin of error, it's 1.96, the number of standard deviations, times the standard error. Okay. Because one standard error is 0.07. I'm trying to figure out how many standard errors is 1.96. So that's why I have to multiply the two. And remember, this is similar to standard deviation. We just use standard error. So we get plus minus 1.96 times 0.07, which is going to be 0.36 plus minus, this works out to 0.1372 approximately, or no, actually exactly, which gives us a confidence interval of 0.36 minus this, which is 0.2228, and 0.36 plus that, which is 0.4972. That tells us our confidence interval. So so what that means is, just one second, we're 95% confident that the true proportion of homes in Flint with prominent lead levels is from a little over 22% to a little under 50%. Which, if you think about it, what was the rule? 10%, right? All of these are above 10%. That seems to suggest that no way, they're violating the rules big time, because we're getting huge proportions when it should only be 10%. Brooke.
Do you want us for?
I'm going to show, let me show you next page.
Okay, I should.
Well, see, no, write a plus or minus, save some time. Yeah. No, you don't need to.
Okay.
Okay.
I didn't.
So the nice thing is, I wanted to, like, for a lot of these confidence intervals and hypothesis tests that we're going to do, okay, I'm going to show you sort of how we do it all by hand. But the nice thing is, and we're going to talk about this in the next lesson. Yeah, I think the next lesson. You can actually do all this work for you on your graphing calculator, where it will calculate all of this for you. You just have to enter certain numbers, and it will spit out a confidence interval for you, as well as some other information you need. Okay, but this is how we sort of do it. I want to show you how we do it longhand before we jump to the graphing calculator. Now this, we're going to be doing a lot of for the remainder of this course. How to answer questions like this. And how we answer them is usually it's a four-step process. State, plan, do, conclude. SPDC. Spiders prefer dark corners. So the question would be this. Construct and interpret a 95% confidence interval for the true proportion of Flint homes that have prominent lead levels. So here's how we would do it. We would go state. We are estimating. Here's the problem. Basically, you're restating the question, or you're restating what's up here. We are estimating the number of Flint homes with prominent lead levels. At 95% confidence. What's the plan? We are going to calculate a one sample. Now, that number of standard deviations that we found on the previous page is referred to as a Z interval. Okay? So this, another way you could see it, it will be, we use Z star times the standard error. So it's a Z interval. Okay. Z interval basically means you're using this. This is how you're calculating your confidence interval. Okay. Okay. Z interval. For the population proportion. If all conditions are met, the planning stage is where your conditions go. Okay. So what are our conditions? Random, 10%, and large counts when we're talking about proportions. The random allows us to use the point estimator. The 10% allows us to use the standard error formula. The large counts allows us to assume it's normal and do that confidence interval formula. Okay. So random. All you have to say, homes were randomly selected. We were told that in the question, or at the beginning. %. Well, how many homes did we sample? 50. And can we safely assume that's going to be less than 10% of all the homes in Flint? I mean, Flint's a city. Okay. So 50 is less than 10% of all homes in Flint. we can make that, it's safe to assume. And the large counts, remember, the large counts is we have to do n times p hat and n times 1 minus p hat, and make sure that those are greater than or equal to 10. So 50, and we had times 0.36. That was 18. 50 times 1 minus 0.36, or 0.64, is 32. Both are greater than or equal to 10. So we can proceed. The do part was what we did on the last page. Okay, but we'll see a little bit later on that the do part is actually just going to be writing what you're going to punch into your graphing calculator. So the do stage is from the previous page. To find the confidence interval, we take a point estimator p hat plus or minus the number of standard errors, which I said at 95% confidence right now is 1.96. I'll explain how we get that, times the standard error. So that's what we did on the previous page. So we had 0.36 plus or minus 1.96 times 0.07, and we're just sort of rewriting what we got on the previous page. And finally, conclude. Remember how we do a confidence interval? We are 95% confident, because that's what we were asked. We were 95% confident. The interval that we just found in the do section, 0.228 to 0.4972, captures the true proportion of Flint homes space with prominent lead levels. Like really the majority of our questions and solutions now will be like this, where we'll be doing the state plan do conclude. Because you're going to be given a problem situation, you got to figure out whether it's a proportion or a mean, and then we got to figure out a couple other things, which I'll talk about later on, and then you go ahead and do your solution. And now, from all of that, use your interval to evaluate whether Flint's water system violates the EPA rule no more than 10%. Well, if you look at this, definitely. Because all the proportions we got in our confidence interval were greater than 10%. So definitely. Because all the proportions in our confidence interval are over 10%. No question. If, say our lowest one was 0.09, then we can't be so sure. Because Less than 10% is a possibility. But because all of these are greater than, we can state with quite a bit of confidence. Okay? So this was our sort of sample study. The actual sample study, or the actual study that they did, I mean, it turned out that the government, the local government or municipal government really failed. Okay? They really failed the town of, I mean, and it was costly in terms of deaths, in terms of sickness, in terms of repair, all sorts of things. Okay. Okay. Thank you for hanging. Oh, look at that, 10:30, just in time for the prefects. Look at that.